Okay, so just a few more things on heat. And just to tie these things back in together, we were just talking about Stevenson here building locomotives to get fish from the ocean to market. Talked about the fact that he made 100 pounds a day, $100 a year about. We also showed that any thermal system, any heat engine, remember the whole title of this book was heat to motive power, so heat engines, any heat engine is going to make entropy. Any heat engine is also going to take a fair amount of information. You're going to have to draw it, you're going to have to think it up, you're going to have to build it, it's in your head, write it down, it's a patent, file it. We talked about the relationship between heat and temperature. We defined efficiency and said that if you want to be more efficient, it's got to get hotter. It's also worth noting this temperature down here on the bottom, this is that's the ambient temperature. That's the temperature within which the heat engine is working. So, any heat engine always going to create entropy. What's entropy? Well, second law, always increasing everywhere. Well, here's the other thing. Is entropy increasing everywhere all the time? It's not. Our own bodies are examples of neg entropy machines. Your house, to a large extent, is a neg entropy machine. If you go buy a Roomba robot, plug it in, sucks up all the crumbs. Now your house is cleaner, less entropy. Well, again, the entropy went somewhere. Somewhere there was a wind turbine spinning, killing a bird. There was a there was a solar panel, enslaving somebody to go dig up germanium in some country. Pick your poison. There was a coal-fired power plant sending CO2 to the atmosphere. So you might have local, you might have this going on locally, negative entropy. Energy had to go in to it. You cooked your breakfast. Now your body is more orderly, more organized than it is. But in the meantime, you fried the egg, or you stuck the toast in the toaster, or you opened the freezer, whatever. So your negative entropy sort of, it's like whack-a-mole. Somewhere some other entropy came out. Does that make sense? Yeah.
Could you define entropy a little more?
Can I define it a little more clearly? Yeah, I sure can. I would love to. Okay. So let's just start here. And a good way to do it is with dimensions. So we know that S equals Q over T. We already know this is energy. We know what that is. It's mass times length squared over time squared. And the weird thing maybe is just temperature. Mm-hmm. So let's see what temperature is. This is kind of fun. So if we do PV equals nRT, that's the ideal gas law. I'm just going to get rid of R, because really all it's doing is keeping track of units. And now I'm going to say that temperature equals PV over N. So this is pressure. This is volume. So again, just think cylinder. I'm going to take it, squish it. If I go down, I get, and you can think of it as a cylinder. You can also just think of it as the weather. There's a cold front coming through. My bones are hurting. There's a low pressure, right? So it could be inside a piston. It could also just be out there in nature. As it turns out, pressure equals force per unit area. That's PSI. If I multiply this by a length, and I multiply this by a length, I get force times length is actually energy or work, and area times length is volume. So pressure is energy per volume. Pressure is energy per volume. It's force per unit area, but it's also energy per volume. Just go and if you don't believe me, just go and, smack your ears. You send a lot of energy into your ears and it hurts. Mechanical energy. So, right there, equals energy per volume over N equals energy over N. Temperature is just energy per particle. And again, just think of little molecules flying around in the air. So, come all the way back up here. Now we know what temperature is. So we've got S equals energy over particles equals N. So at the end of the day, entropy just equals some number. That's what's sometimes kind of hard to think about. But if you go out, there's a couple kind of cool videos out there.
Sum is in the sum of all, or sum is in any?
The sum of all, the SUM of all.
Do you know how many people were in that panel that Steve Vernon was a part of that received the Nobel?
IPCC? I don't know. I would guess there's maybe 50 or 100 people on the IPCC. I'm not going to spend lecture time on this, but go out and look at Maxwell's demon. These little curves right here, see these little curves in the background? They're basically showing you that some of the particles are moving fast and some of them are moving slow. So the colder things get, the less likely you are to find something moving fast. So at the end of the day, entropy is just how much disorder there is in the room. So just imagine, bugs crawling around on the floor, or like something you can actually see, or an explosion, like, oh my gosh, everything's going everywhere, versus something moving gently and gracefully. So I wish I had a better answer, but at the end of the day, that's really all it is. It just comes down to a number.
Okay.
Yeah. Okay, let's see what else we got.
Even just considering like a bug crawling on the floor would distract you from moving faster with your thought patterns to get to the point, or
I suppose, yeah.
get to where you
Yeah,
need to go.
well,
The bug
and then-
will get in your way and stop you from moving anywhere.
Yeah,
Oh,
but there's an optimum there. Talked about whether you're more creative or productive if you have a messy desk versus a clean desk. So
Yeah.
okay, and so here's just a few examples. Next week, or I guess on Thursday, we'll get into these stationary steam engines. We'll get into steam turbines, but for now, one thing notable is that all of these levers, they're taking reciprocating motion. This is reciprocating motion, right? Those are the pistons we've looked at, and turning that reciprocating motion into rotational motion. That's what all these levers are. That's why on the locomotives, you can't. Well, you can just see the bar right here. So the chugga chugga, the back. There's no turbines in this thing. It's all cylinders of steam going up and down. So you're taking reciprocating motion and turning it into rotational. That's the whole point there. And like I said, on Thursday we'll get into turbines, where you sort of skip the reciprocation part. It's just everything's spinning in a line. Okay, so there's we covered a lot. We covered a lot today. We didn't do any specific math problems. Maybe I'll torch you with one of those on Thursday. But go ahead, finish up your summary one if you haven't. finish up and submit your summary 2, please. What else? Finish summary 1, finish summary 2. Go ahead and read the rest of this chapter, and I will launch exam 3 on Thursday. Exam 3 covers chapters 5 and 6.
Meaning launching it, you'll just open it up for us?
Yeah, in fact, I think it's already sitting there in Moodle.
I think, yeah, I've seen the
Open.
Moodle.
Yeah, it's sitting there ready to go. It'll deploy on Thursday.
Cool.
Yeah. Thanks, everybody.
Thank you, have a nice day.
I will, thanks.